energy. So you've heard this in a previous talk that we only consist of 5%. So our hands, our feet, our faces, this room, the stars, everything you see, everything you've interacted with, the dust, the gas, everything in the universe that is visible, even the invisible stuff like neutrinos, all of these particles and waves and matter and energy consist of only 5% of the universe. It turns out that 26.8% is dark, doesn't interact with the electromagnetic photons, and we cannot see it. We can only infer that it exists because it interacts gravitationally. So you see effects of this huge amount of matter because it affects our ordinary matter gravitationally, but in no other way. And then we have the rest of the energy and the matter, and the constituents of the universe is dark energy. It's about 70%. So first I'll start talking about dark matter. It's about a quarter of the universe. And we can see these galaxies. This is ordinary matter. This is a photo of Andromeda. So right in the center is where all of the stars and everything has attracted. And so you have the highest density of matter right in the center. And then as you get further and further out, you have less and less. But it's all gravitationally attractive. So gravity pulls everything together. So these stars out here are being pulled in by the center, and the center is actually being pulled also out by those stars. And if you look at the speeds with which these velocities of which these stars are rotating around, you would expect really fast rotation speeds in the center, and then they would get slower and slower as they get out in order to stay in orbit. Okay, so if you have some kind of a planet swinging around, I'll demonstrate here. If I don't break something. You have like a planet swinging around. So my hand would be the center of the galaxy holding these stars going around. And if the stars go too fast, they'll just escape the gravitational field, right? So they'll go out. If they go too slow, then they'll kind of spiral into the center of the galaxy. So there's a fixed speed that it has to go in order to stay in a fixed orbit. And as you go further out, the planets feel less of the gravitational field, so they have to go less fast, right? So if you look at the speeds of galaxies, of stars going around galaxies, you'd expect this curve here. So as you get further away from the center, you expect the speed of the stuff in orbit to decrease. But actually, what people measured is kind of flat. So what that tells you is that there's a lot more mass, a lot more matter in the universe that's pretty much the only way you can explain this measured velocities way out here. So the way they measure that is typically by redshift. If you have something that emits light traveling away from you, the frequency of the light kind of gets stretched. And if it's coming towards you, it gets contracted, so you have a higher frequency. So this is a blue shift. Okay, so you have red shift on one side, blue shift on the other, and then from there you can measure the speed that the objects are traveling. So this was first measured, first proposed in 1932 by Jan Oort. And so this was pretty revolutionary at the time. This was 1930s, a long time ago. Then the explanation was there's some kind of matter that we don't see. It doesn't emit any light, reflect any light, doesn't change the path of any of the photons behind it. But the galaxies must be embedded, completely surrounded by this other matter. So then, a year later, they started looking at pictures of galaxy clusters. So before we were talking about just one galaxy. Now in this photo, each of these golden ellipses here is a galaxy, and this is a cluster of galaxies. And then, so these gravitational effects pull the galaxies together and they form clusters. And then you have the galaxies within the clusters orbiting around the center of the cluster. So then if you look at the rotational velocities of the galaxies going around, you find the same effect, that farther from the center, the speeds are much too fast and the clusters should just fly apart. But there's some kind of mass, some kind of matter there that's holding it together. So galaxy clusters must be embedded inside some kind of massive dark matter that we can't see. So this was proposed in 1933, just a year later. And now it'd be great if we could see the dark matter, but we can't because it's dark. But there's a way that maybe we can get more evidence just besides the velocities, but actually looking into the sky. So light travels in a straight path. It travels straight through space. But what happens if space is curved? Then the light curves through the space, still going straight through space, but space is curved. So Einstein said if you have a big mass, it's going to curve space. So you have a star, it's shining its light like this, and then it curves, and then it hits Earth, and then we see it. But we see it when we look in this direction, so we think the star is over here, right? So what happens with the light that goes down this way around the star? It gets deflected up towards Earth. So do we see two stars when there's actually one? The answer is yes, we could see two stars. But what about the light that comes forward in front of the sun or behind the sun? So what we could actually see is a ring. One galaxy or one star being distorted by a large amount of mass can produce these strange effects. This ring, it's called Einstein's ring by astrophysicists. So in this image, instead of the sun, we have a cluster of galaxies. So this is much, much more massive. And then the light distorts in the same way. So this is just an illustration, but do we have something here on this Earth that would mimic or replicate the effect of the distortion of light? And the answer is yes. We can take a wine glass, and you have just one object, say one galaxy or one star, and you put something like matter, like a lens, a glass, in front of the flame, single flame. And if it's directly behind it, then you see this ring. If the mass is somehow tilted or off-center a little bit, you can see the ring becomes distorted. So you can see 3 points when actually there's only one, or 2 points. And you see these arcs that are kind of stretched and bent. Okay, so you can do this at home. It's called gravitational lensing, but you're just using a wine glass. And here's an actual photo from Hubble Space Telescope. And so these golden ellipses here are galaxies inside a galaxy cluster. And these stretched lines are the galaxies that are far, far behind the cluster that get distorted by the mass inside the galaxy cluster in the middle here. So right now, we're looking at dark matter, in a sense. We're looking through dark matter and seeing the effects through gravitational lensing. So let's review some evidence here for dark matter. So the orbital velocities of stars are too fast to keep the galaxies together. The orbital velocities of the galaxies themselves inside galaxy clusters are too fast. And there's gravitational lensing effects. If you calculate the mass that should give you the lensing effect from that picture that we just saw, there's much more mass required to produce the stretching of the galaxies that you see. So you can calculate the amount of dark matter that's there. So dark matter is 26.8%. It forms the backdrop of everything. So all the stars and galaxies are embedded inside of this matter. So they're like the little lights on the Christmas tree. The dark matter is the tree. It holds everything together. And then these lights are just coming along for the ride, basically. Okay, so this is the evidence for dark matter. And then we can switch to dark energy, which is much more prevalent when you look at the constituents of the universe. In order to talk about dark energy, we have to talk about space itself. So in the 1800s, scientists thought that the whole universe was just the Milky Way galaxy, our galaxy. They didn't see, the telescopes weren't good enough to see outside of the Milky Way. Then in the early 1900s, we started to notice that there are other galaxies outside of our own. Meanwhile, Einstein was developing his theory of relativity, and he was writing down the equations, and he got to the end, and he saw that on one side of the equal sign couldn't equal the other side of the equal sign until you put this extra term, this energy term, that would balance the equation, that would create a universe that was in a fixed box of a fixed size. So he wanted a static universe. And he put in this energy term, and it made his equations work out just perfectly. But the equations were unstable. If the value of this cosmological constant that he put into the equations was just a little bit lower, just a little bit higher, the universe would either expand or contract. And all the data he had up until that point said that it was pretty much fixed. Okay? So he said that the constant is equal to the value that just set these equations equal, and you have a stable universe. 2 years later, Hubble discovered that the universe is actually expanding. So Einstein said, oh, this is my biggest mistake. I made a blunder. I could have predicted this from my theory 2 years earlier. And so he regretted that his whole life, that he didn't make this prediction. But it turns out that his equations were right, and he can put in a value of this parameter that would explain the expansion of the universe. Okay, so at the time of the Big Bang, the universe expanded really fast. Okay, there was this big explosion. And then there's gravitationally interacting stuff inside the universe, inside the space. So each universe is pulling on each other. So everyone thought that this expansion should be slowing down, that you have one universe pulling on the other, even though it's expanding, but it should be expanding at a slower and slower rate, okay? And so I can have another demonstration here. This is the universe, okay, which is too big. I can't hold the whole universe. Maybe, can someone hold on? Maybe you can hold on to that. Okay, so if you pull, you expand the universe, you see that each galaxy is getting further apart from each of the other galaxies. I don't know if everyone can see this. Okay? Now, let's say we live in this galaxy. Okay? If we expand the universe, this galaxy is getting further away, and that one, and those are getting further away faster than this one is. So the further you look, the faster they go. But if we're this one, you'll see the same effect, that this one's moving faster than this one. Okay, so it doesn't matter where you are. Thank you very much. It doesn't matter where you are in the universe. The galaxies that are further away from you move away faster than the galaxies that are closer than you are. So we're not in the center of the universe necessarily, but the further away you go, the faster away everything is moving. Okay, so that'll be important later. But here's the question. Is space slowing down fast enough that it'll stop, slowing down so fast that it'll reverse? Well, they decided to measure this, and we didn't get the result until 1998, so only about 15 years ago. And the result is really strange. It's actually accelerating, okay? So what the scientists did is they took supernova, type 1A supernova, which have a fixed brightness, okay? So let's say you have a 100-watt light bulb, and you put it right in front of your face. It's really bright. But then you put it a kilometer away, and it's really dim, right? But we know that it's still 100 watts. So the same thing with these supernovae. So you can measure the distance based on the brightness, because you know that they're all the same brightness when you're really close to them. Okay, so they use these supernovae to measure the speed at which the galaxy is expanding. So really far away from you, the light emitted from the supernova is older because it takes all that time to reach you. Okay, so the speed at which the older ones are traveling is different from the speed at which the new ones are traveling. So you can see, is it expanding faster in older times or faster in more recent times? Okay, so they were awarded the 2011 Nobel Prize for this, and it's very interesting. So now you can take Einstein's parameter that balances his equation and just give it a different value based on the measurement that they made. And that will give you the accelerating universe. It turns out that parameter had units of energy. So that's why we call it dark energy. We can say that the amount of stuff that's causing the expansion of the universe is energy because of the units in the parameter in Einstein's general relativity. So another measurement that was done that points towards dark energy is the measurement of the cosmic microwave background. So if you measure the background radiation in all directions, you see that there's not much fluctuation. So this is another standard candle, kind of like the supernova. Okay, so you have a fixed amount of deviations or plus or minus differences that you would expect. And if you had a flat universe, then you would expect kind of uniform deviations, so pretty much flat. If the universe was curved or had some global curvature, as you pass through space and it comes towards you, those standard candles would either get stretched or contracted, and you'd see some parts of this distribution would be much larger than other parts. Okay, so maybe this side would all be red and this side would all be black or something. But you see a pretty much flat universe. So this couple of years ago produced results that give you 72, 22, and 4.5%. And then last year, in 2013, the Planck results were published, and that gives you a much more precise value of these numbers. So you see that the Planck results are much more finer. They have less uncertainty than the previous measurement. So we get a better calculation. So these numbers come about because you can put into the formula for the mass energy density of the universe what you need, what you require in order to have a flat universe. So we measure that the universe is flat, and then we calculate how much energy we need in order to have a flat universe. And it comes out to these numbers here. Another independent result, so not using supernova at all, is the Wigglesea experiment in 2011. They studied 200,000 galaxies, okay, and they studied this large-scale structure. So you have galaxy clusters, and they're surrounded in dark matter and dark energy. And if you have this large-scale structure, according to what they found from these 200,000 galaxies, it's telltale evidence for dark energy, independent from supernova. So we have two experiments, many experiments, who confirm the same result. Okay? So let's review the evidence for dark energy. The expansion of space is accelerating, and the theory requires more energy to form a flat universe. So these are the two basic things that we've found that imply the existence of all of this dark energy. So now we can review the properties of each. Dark matter is dark, so we don't see it. Okay? But we're pretty sure that it consists of some kind of particles. Some kind of particles that we have, electrons, protons, neutrons. We have our particles. We think that there are dark matter particles. So pretty much the same way, or very similar to how our ordinary matter is built up, we think that dark matter exists in the same way. It exerts gravitational influence, just like our ordinary matter does. And it clusters together, and it forms these halos of dark matter that exists around the other ordinary matter. So it encourages the growth of structure, and it comes together and forms these strong bands of dark matter in the universe. And it dilutes as the universe expands. So when you stretch the universe, okay, each bit of dark matter gets further and further apart from the other bits of dark matter. And so eventually, if it goes out forever, it will be infinitely far apart from each other bit of dark matter, and there will be nothing left, just like we won't be here. So dark energy is also dark. We don't see it. It puts more space between galaxies. So this dark energy causes this accelerated expansion of the universe. So putting more space in between the galaxies makes the galaxies feel less gravitational pull on each other. It's not anti-gravity, okay? It doesn't reverse the effect of gravity. It just makes them further apart, so they feel less gravity, okay? It's important to know that the galaxies aren't moving through space, okay? They're fixed in space at a fixed point, like they're pinned here to this thing, right? It's the space that's expanding itself, not the galaxies moving through space. Oh, I went ahead, didn't I? Okay. So the other thing is that the dark energy is smoothly distributed. It's not clustering like the dark matter does. And it's persistent. It doesn't dilute as the universe expands. So each little bit of space that is created in the expansion has more and more energy. So this is a really big problem, because we have these conservation laws in physics that say there's a fixed amount of energy and it's not created, not destroyed. But if we're making more and more space, then we have more and more of this dark energy. So this is a big question that we don't know the answer to. So we know that dark energy is smoothly distributed. So it's pretty much everywhere. And we know that it's persistent, so it doesn't dilute. This term in Einstein's equation that balances the energy that we need to form the accelerating universe is perfectly smooth and absolutely consistent. There's no fluctuation. So We're not sure if this is really the answer to what dark energy is, but we know that it's along the same line. So it should, for measurements, it's kind of smooth and pretty persistent, but we don't know if it's exactly 100% smooth and persistent. But right now, the cosmological constant in Einstein's equation is the best thing that we have to describe it. We still don't know why it should be there. Why should this value exist in his equations? Why should it be so small, and why it's not 0? Okay, so these are open questions of dark energy. I want to also emphasize that dark matter and dark energy are completely different things. The only thing that they have in common is that they're dark. Okay, so you have E equals mc squared, right? Well, E for dark energy does not equal dark matter times c squared. So they are completely different things. You can't say dark energy equals dark matter times c squared. It's different things. Okay, so we kind of know what maybe dark energy is. It's this cosmological constant, the cost of having space itself, how much energy there is in the vacuum of space. We don't know why it should be there, but we think that's what it is. Dark matter, we're not really sure what it is, but we have other theories from particle physics that predict the existence of some particles that don't interact very much and are very massive, that would account for this large mass of the dark matter. So it's nice that we have an external theory that could make a prediction for these things that could be the dark matter, but we haven't detected them yet. So we are now on the search for dark matter using several experiments that are tuned to detect what these other theories predict the particles could be. So some theories give typical densities and energies, and so we can gear our experiments towards the search for these weakly interacting massive particles. It doesn't mean that they interact via the weak force that was mentioned in the previous. It's just that the strength of the interaction is very small. Okay. So here in Italy, in the Gran Sasso Laboratory, we have this dark matter project. They use large sodium iodide detectors to search for these WIMP particles coming in and hitting their detector and causing some kind of a recoil or interacting in their liquid xenon scintillator and producing a flash of light. So all of this whole bunch of experiments are being developed to search for this, one of these 25% of the universe, much more than all of the other stuff that we've studied up until this point. So we have another experiment called the cryogenic dark matter search. Started in 2003. It's a series of measurements. It was part 1, part 2, and then the super CDMS. This is located in the United States in a old abandoned mine about in Sudbury. Oh, now it's in the United States, and next year they're thinking of moving it to Canada into a much deeper mine. So in order to observe these particles that don't interact very much, you can't have a lot of backgrounds from the stuff that does interact a lot. So if you go underground, you can measure without background effects. Okay. I should mention that the DAMA project measured annual modulation. So if you have a flux of dark matter all around say the solar system, our solar system, and then the Earth goes around the sun, at some point, okay, the galaxy is also going around. So at some point, the Earth is going faster through this flux of dark matter than it is on the other side coming around in the orbit. So you should see, in one half of the year, you should see more interactions than in the other half of the year. So you see some kind of an oscillation and an annual modulation. So every year in June, you see more than you see in December. Okay, so there's another experiment in South Dakota, United States, the Large Underground Xenon Experiment. This uses a time projection chamber I don't know if someone else talked about these types of detectors. Their first results were last year. They did not see a WIMP particle, but they can put limits on the interaction or the density of these particles, and so therefore influence the theories that predict them. So this is a list of some of the dark matter experiments. I think there are more. So my particular research here is looking for a dark photon, which would be a force carrier in the equivalent dark zoo of particles. And if it possibly interacts with our photon in some mixing way between our ordinary matter and the dark matter. So I didn't put that on the list. So there's definitely a lot more things going on in the world nowadays about dark searches. So I'll end with that. We don't know what 95% of the universe is. So thanks. Are there any questions?